Welcome to our Chemistry 1411 final exam review. And we are probably, in all likelihood, not going to have time to go through the entire final exam review. So what I would like to encourage you to do is, if you have any questions over the final exam review, any questions or any particular topic you'd like me to go over, let me know what the topic is, and we'll go over some practice questions on that particular topic. And I don't mind if we bounce around. I also don't mind if we go in order, so just let me know what you want to do. Just as an FYI, the answer keys to all of these are up on our website. So, can y'all see where it says Chemistry 1411 practice tests?
Yeah.
Okay. Yeah, I know you guys can. But so yeah, under chemistry, under the chemistry resources main page, if you go down to Chemistry 1411, in addition to all the other really cool resources, you can just go to you can go to practice test, and there's practice test from Dr. Chibuni, practice test from Dr. Segal. The one that we're going to be using is the practice final exam from Dr. Segal, and the answer key that's posted here is comprehensive and it has all the work shown. It's actually pretty nice, if it'll ever show. Try it again. Open. Yeah. So you can see all the work is shown for the ones that do require work, etc., etc. So, skip that. Let us go ahead and begin. So, what would you like me to cover first? What should I start with? I could start at the beginning and go forward, or I could maybe start at the back and go reverse and go in reverse order, or I can jump around. Any suggestions?
You could jump around.
Okay. All right, let's go ahead and do that. Let's see. Forgive me. Okay. So I don't know if we really covered this. So I'm going to skip those last part. I don't think you guys got to intermolecular forces yet, have you? Yeah.
No.
Ideal gas law. Okay. So let's maybe start with something like this. It says a sample of gas 5 moles at 1 atm is expanded at constant temperature from 10 liters to 15 liters. The final pressure is what? With these gas laws, there's really only 2 gas laws that you actually really need to be concerned about. And that is, the first is PV is equal to nRT, which is the ideal gas law. You would use this equation when you have one set of conditions. So what do I mean by one set of conditions? One pressure, one temperature, one volume, etc. If you have 2 sets of conditions, then you'll use some part of the combined gas law. And I'm going to actually use a more, shall we say, extensive version of the combined gas law than you're used to seeing. But it's basically P1 V1 over N1 T1, and that's equal to P2 V2 over N2 T2. Now the thing about this particular combined gas law is if there's anything that's constant, if there's anything that doesn't change, you can kind of ignore it. So, like for example, in this case, it says the gas is expanded at constant temperature. So that tells me if I can actually cancel out and ignore the temperature. Okay? It also tells me that the sample of gas is 5 moles. Now it says it's expanded. Is there any indication that the number of moles is changing here? No, so chances are that I can ignore this as well. I can ignore the number of moles as well. So it looks like we're going to end up using P1 V1 is equal to P2 V2, and I'm looking for the final pressure. So that I could basically, one thing I like to do is I like to actually list out my variables. You don't have to do this, but I do find that for those who do this, it does help prevent mistakes. So P1 would be what? 1 ATM. V1 would be what? And P2 is what we're looking for, right? And V2 is 15. Now, just out of curiosity, could you have a situation in which the volumes are in different units, like one's liters and the other is milliliters? Yeah, you could. Could you have a situation in which the pressures are in different units? Yeah, so you always have to make sure with this particular formula that the units match. So the volume units have to match and the pressure units have to match. Otherwise, it won't work. So in this case, I go ahead and plug in my thing, 1 times 10 divided by 15. And that's going to give me about 0.67. Essentially, I can erase this bottom part since I don't need it. And then I'll just to solve for P2, I'll divide both sides by V2. That will cancel out this little algebra solving for the variable that I don't know. Get it by itself, and then plug in your numbers and solve, and you're good to go. 45 is also a really good one. The hybridization of the central atom in XCF4. Now for that, you'd have to actually draw the Lewis structure. Whenever you're trying to figure out hybridization, you want to draw the Lewis structure. Do you want to go over that together? Do you want to take a minute to try to draw the Lewis structure, and then we can check it together? What do you think?
We could do the second option.
Okay, let's take a minute to have you work it out, and we'll get together. And I'm going to give you 2 minutes. I think you'll be able to do it in 2 minutes. Draw that Lewis structure for XCF4. Okay. Let's go over it. So the first thing you do, and let's just kind of review the steps. Some of you may already know this, but for those of you who don't, this will be helpful. So the first thing you want to do is count the total number of valence electrons. Xenon's a noble gas, so it should have 8 valence electrons. Fluorine, if you look at its position in the periodic table, it is in that column right before the noble gas. There should be 7 valence electrons. There are 4 of them, so 4 times 7. And if I go ahead and 4 times 7 is 28 plus 8, that gives me a total of 36. So this is how many valence electrons I have for bonding. The next thing I do is I draw what's known as a skeleton structure. Essentially, I just show how the atoms are connected. XCF4 means xenon is connected to 4 fluorine atoms. Put 1 on each side. Now, in the process of putting 1 on each side, I've already used 8 electrons. We'll subtract 8, and that's going to give me 28. My 28 valence electrons now, I'm going to go ahead and place in pairs around, starting with the outer atoms. So, fluorine. Ooh, actually, I'm going to do this. It's going to make it easier. Thickness, I'll make it fat. There we go. Whoa! That's a little too fat. There we go. I like that better. Erase this. There we go. Draw. There we go. So 2, 4, 6, 8, 10, 12, 14, 16, 18 so far. 20, 22, 24. Redo these. There you go. I still have 4 more that I need to place. No other place to put them, so I'm going to have to put them on xenon. So you're going to end up with something that kind of looks like this. How many electron domains are there around the xenon? Not 4. What'd you say? 6. Yeah, because the electron domains, remember, the electron domains are essentially every single bond, every lone pair, every double bond, and every triple bond is an electron domain. A double bond is still only 1 electron domain, and a triple bond is still only 1 electron domain. In this case, I have 4 single bonds and 2 lone pairs. So this is a total of 6 electron domains. You'll hybridize the number of orbitals for which you have electron domains. So 6 electron domains, 6 hybrid orbitals. There's 4 electron domains, 4 hybrid orbitals. And in this case, if I need to hybridize 6 orbitals, that means the hybridization is, sp3d2. Yep, this one. Very good. And the reason it's sp3d2 is because if you remember your electron configuration stuff, remember when you're doing the electron configuration, there's s, and then the p orbital has 3, p subshell has 3 orbitals, and then after that comes the d, right? See, I can only have sp3. I can't have sp4 because there's only 3 p orbitals. After that, I have to dip into the d. All right, cool. What's another good one to do? I like polarity because everybody has trouble with polarity. All right. Yes? Yeah, shall we do a polarity?
Yes, please.
All right, so it says of the molecules below, only blank is nonpolar. So let's look at these molecules. If you're doing your Lewis structures, the only way you can really determine if a molecule is polar or nonpolar usually is by drawing the Lewis structure. The only exception is a 2-atom molecule. For a 2-atom molecule, the only one we have here is HCl. 2-atom molecule, the polarity of the bond is the polarity of the molecule. In other words, if the atoms aren't the same in a 2-atom molecule, it's probably polar. HCl is definitely polar, right? But what about TeCl3? Would that be polar or nonpolar?
Polar?
It would be polar. If you look at the Lewis structure, tellurium actually has 6 valence electrons. Chlorine has 7. So if you actually if you did the Lewis structure here for tellurium dichloride, it would look like this. Now, this might not initially look as though it's polar, but what you have to remember is that this is 3-dimensional. It's 4 electron domains, so it has a tetrahedral formation. And with the tetrahedral formation, if you have 2 lone pairs, those 2 lone pairs are always going to be more on one side of the molecule than they are on the other. In fact, as a general rule, the only time you have if you have lone pairs in the central atom, it's always polar, except for 2 very rare circumstances. One is if you have something like XCF2, and XCF2, you would actually have 2 bonding domains, and then you would have 3 lone pairs. Normally, this is a trigonal bipyramidal, electron domain geometry. And since the lone pairs are at 120-degree angles to each other, they are in geometrically opposite positions. This molecule is therefore linear, and it ends up being nonpolar. But it's very rare to see something like this happen. You do not have many compounds that will have 3 lone pairs and 5 total electron domains. That's one way in which it could be nonpolar. The only other case is if you have 2 electron domains with 6 electron domains with 2 lone pairs. And an example of that would be xenon tetrafluoride. So xenon tetrafluoride would look something like this. It's actually square planar because you have a lone pair of electrons on the top and a lone pair of electrons on the bottom. And they're in opposite positions. So that ends up canceling the effect is that there's no net dipole moment. They all cancel out, and you end up with a electron domain geometry that is square planar, and therefore it's nonpolar. So of these, which one of these would be nonpolar? I can't quite hear you guys back there, so if you want to make an answer, make it confident. H2O is a total of 8 valence electrons, right? So you have 2 hydrogens and 1 oxygen. So I've already used 4, so I have 4 more left to use. I have 2 lone pairs and 4 total domains. It's actually going to be a bent molecule. Is that going to be polar or nonpolar? Yeah, water is the kind of the definitional polar molecule. If you have biology, they're always talking about how water is so important because it is polar and it's a kind of universal solvent. So the ones we've looked at so far are polar. That only leaves NH3 or CO2. What do you think it is? CO2. CO2 is nonpolar. And the reason is because it has 2 double bonds and no lone pairs in the central atom. If there's no lone pairs in the central atom, then the molecule will be nonpolar if the outer atoms are the same. And in this case, the outer atoms are the same. They're both oxygens. Any questions? Good? Yeah, remember those 2 quick rules for determining polarity. If the central atom has lone pairs, it's polar unless the lone pairs are in opposite positions. Okay? So basically, 1 lone pair in the central atom is automatically always polar. You need at least 2 or more, and it's pretty rare. So if you had to guess, if there's lone pairs in the central atom, it's probably polar. And then, if there's no lone pairs, are all the atoms bonded to the central atom the same? If they are, nonpolar. If they're not, polar. Yes?
I've seen another one like that, but it was like 3 or 4 atoms.
Like which one?
It was like CCO8. It was like 3 or 4 atoms around here.
Oh, okay, like something like this. Like, okay, let's say you had CHCl3. Let's say we had something like that.
Yeah, like that.
And actually, let's actually make it even more interesting. Let's say it's CH2Cl2. So dichloromethane. Would this be polar or nonpolar? Say polar?
Nonpolar.
It's actually polar. Even though it looks like and I know you're thinking, because technically speaking, it's based on the net dipole moment, right? I know you're thinking, oh, well, chlorine's more electronegative, so this is going to pull this way, this is going to pull this way, and then this is going to be pulled down this way, and this is going to be pulled down this way. Well, those arrows cancel out. But the problem is, this is not square planar. This is tetrahedral. So those two chlorines are always going to be more on one side, and the two hydrogens are always going to be more on the other. So that's why I say for that simple rule, if all of the atoms bonded to the central atom, if all of them are not identical, then it's going to be then it's going to be polar. If they are all the same atom, they're all H's, or they're all Cl's, or they're all oxygens, then it's going to be nonpolar. They're all the same. If even one is different, then it's polar. Cool?
There's no exceptions to that?
There's always exceptions. None that you need to worry about. That's true. You know, the interesting thing is you can actually have a non-polar you can have a polar compound with non-polar bonds, and you can have a non-polar compound with polar bonds. Let me show you an example of that. O3, ozone, is actually a polar molecule, interestingly enough. And the reason is because it has a lone pair on the central atom. Even though the individual OO bonds are nonpolar, because they both have equal electronegativities, because of the arrangements of atoms, because of that lone pair of electrons on the top here, that provides a certain concentration of negative charge, and that actually makes this molecule polar. So polarity of bond and polarity of molecule are not the same thing. So you have to apply those rules, identify if there is, to identify if it's polar or not. Okay, cool. What else? What else you want to talk about? $49? Ooh, this is a fun one. Okay. So ammonium nitrate, and if, by the way, if you need me to go back and look at something, or if I move too quickly, just stop me and I'll go back. Especially you that are connected with me online. Okay. So this one says 49, ammonium nitrate undergoes thermal decomposition to produce only gases. What volume of gas is produced by the decomposition of 35 grams of ammonium nitrite at 525 degrees Celsius and 1.5 atm? Okay, so this is interesting. What you need to actually do is throw down some stoichiometry. So there's a couple of different ways to approach this, but you can go ahead and approach, I think probably the way that makes more sense here is to do the stoichiometry first. So I recognize that I have temperature and I have pressure, and it's all one set of conditions, right? So this is probably going to be a PV is equal to nRT situation. But I also recognize it's wanting me to figure out the total volume of all gases, not just one of them. So what I'll do is I'll start with my 35 grams. 35.0 grams of NH4NO2. And then I will convert the grams to what? Moles. Very good. Before I do that, I have to calculate the molar mass. So 2 nitrogens, 2 oxygens, 4 hydrogens. 28, 32, 64. Sorry. Go ahead. You confirm me, because my mental calculator isn't 100% accurate. I would say it's 64.06. What'd you get? Yeah, it kind of depends on if you use 1.008 for hydrogen or 1.00 or 1.01. But yeah, no, that's good. Told you 64. And honestly, for a multiple choice test like this, none of these answers are close enough that you really have to worry about doing anything beyond 64, right? So you could say 64.06 or 64.04, but you could also just use 64. And this is going to give you 1 mole of NH4 and O2. Now here's the cool thing. To use this equation up here, the PV is equal to nRT equation, if I want to solve for the volume, V, what piece of information do I have to solve for here? Because I'm given the temperature, right? And I'm given the pressure. What other variable do I need? Well, you do need the R, but that's a constant, so that's something you'd either be given or you'd have to memorize, right? Well, the temperature is given too, right?
Or you have to convert it to Kelvin.
Yeah, you have to calculate. Well, you have to convert it to Kelvin. You're right. Well, what else do you need? The moles of gas. That's the one piece you're missing because you have the pressure given, you have the temperature given. R is a constant, so you kind of have that. You're solving for V. You need to find N, the number of moles of gas. So in this case, since I want the moles of all gas, I could say, okay, well, moles of NH4NO3 on the bottom, what would I put on top?
3.
3. Now you could do it the long way and repeat this calculation twice, calculate the moles of water and gaseous water and the moles of nitrogen, or you could just do it all together at once and just say, okay, well, 1 mole of ammonium nitrite, is going to give you 3 moles of gas. Because there's 1 N2 and 2 H2Os. Those are the different, so for every one of these, I get 3 moles of gas. Does that make sense? Nitrogen's a gas, and I have 2 water, well, so basically every molecule of NH4NO2 is going to produce 1 molecule of N2 and 2 molecules of H2O, yeah. So then all I have to do is calculate that, and once I do that, I can solve for the volume. It's just going to be nRT over P, the pressure. Now, what is the number of moles here? If you calculate that. What did you say? 1.65. All right, 1.65. So I got 1.65 is my number of moles. And then my R value. Now, remember, the R value has to match the pressure unit. So what R value would I use if my pressure is an ATM?
0.02.
Yep. 0.08206 liter ATM per Kelvin mole. Just out of curiosity, does anybody know what it would be with millimeters of mercury or torr?
8.341.
It's actually 62.4. But for kilopascal liter per Kelvin mole, it would be 8.314. Liter ATM per Kelvin mole. Usually your professors will only give you one of these constants. They'll only give you this one. And so you'll just have to convert the pressure units. Just know that like 760 torr is equal to 1 ATM. And 101.3 kilopascals is equal to 1 ATM. Although, honestly, I don't really see professors or any instructors using any other pressure units other than torr or MMHG is the same thing as torr. Yeah, MMHG, torr, or like ATM. Usually that's all I see them use. And then the temperature, as you correctly ascertained, needs to be in Kelvin, right? So I have to add 273 to that bad boy. That's going to give me 798. 798 Kelvin. And then all I have to do is divide that by the pressure, 1.5 ATM. And if I do that calculation correctly, what do I get? What do we get? 72? That sounds about right. There we go. That's good. That's a tough question. Do I expect her to give you a question like that? Probably not. To be honest with you, okay. I don't know. I thought she was getting easier in her old age. You know. There's shame on me. I shouldn't say that. Oh my goodness. I'm sorry to hear that. Okay. What next? Yes. What kind of reaction? Enthalpy of reaction. Absolutely. Okay. Let's bounce around to enthalpy. Okay. Okay, this is a good one. 24. Says the value of delta H for the, and you also want maybe another problem that deals with Hess's law. Oh wait, I don't see a Hess's law problem here. I might have to go over one of those separately, but this is an enthalpy of reaction problem, number 24. So in this case, when it says the value of delta H for the reaction is negative 790 kilojoules per mole, the enthalpy change accompanying the reaction of 0.95 grams of sulfur is what? Okay, so what you have to recognize is that when you're given an enthalpy of reaction, like this negative 790, that is indicating the amount of heat that would be released or absorbed when the molar amounts here are reacted. So in this case specifically, 2 moles of sulfur reacting with 3 moles of oxygen to produce 2 moles of sulfur trioxide would release 790 kilojoules of energy. Does that make sense? So that means you can use, and actually if you want to, when it's exothermic, is heat a reactant or a product?
A product.
It's a product. It's a product, yeah. Because when think about it, like if it's exothermic, that means heat is released, it's produced, right? So it's a product. If it's endothermic, that means heat is absorbed, it's taken in. It's a reactant. Does that make sense? Yeah, if the delta H is negative, that means it's exothermic. It means the heat is released. If it's positive, it's endothermic. Now, why is this useful? Because the truth is, you can actually treat this like this. You could actually look at it like this. In this case, we'll stick with this because there's a bit of a semantics problem with these thermochemistry problems. It's one of the things that drives me crazy. But if it says enthalpy change, it can be either positive or negative. But if it says how much heat is absorbed or how much heat is released, can your answer be positive or negative? No, it can only be positive. Even if it says how much heat is released. Because you can't release a negative amount of heat, right? Just like you can't It's kind of like the difference like this. If 3 of you were to get up and walk out, I could say the change in the number of people attending this session is -3. It's the change in the number of people. But I can't say there was -3 people who came into the session. See what I'm saying? You can't have a negative person. You can have a negative change, but you can't, well, I mean, you can have a person with a negative attitude, but you can't have a negative person. Yeah, you know what I'm saying. But there you go. So let's go ahead and 0.95 grams of sulfur. Now, what's the first thing I'm going to want to do with this?
Get the moles.
Yeah, you got to convert to moles. So I got grams of sulfur. I'm going to convert it to moles because it is the equation. The equation is giving me the molar amounts for this. So when I'm converting grams to moles, how many moles is it? How many moles? 1. Grams to mole conversions are always 1 mole. So this is going to be 32.07 if you look at your periodic table, or 32.065. Doesn't matter too much. And you could even just use 32. But now I can convert moles of sulfur to kilojoules. Okay, big warning to y'all. Notice what I did here. I always put my units on top and bottom first before I ever put any numbers, okay? Unless you know what you're converting from and what you're converting to, there's no way you can relate them because the top has to be equal to the bottom. Now, how many kilojoules is equal to how many moles? According to the equation. Now, technically speaking, because this is an enthalpy change, even though I know that this is 790 kilojoules of heat that would be released, I'm actually looking for the enthalpy change. So I'm going to use the -790 here. So -790 for how many moles of sulfur? 2. And then I'll just go ahead and multiply everything on top and divide by the bottom, and I'll get my answer. And it should be something. Yeah, -23. Cool? Or did you get something else? Oh, somebody forgot to divide by 2. Yep, I'm trusting you guys. I'm trusting you guys. You let me down. Just kidding. Let's double check. 24. It is C. Yeah, it's -12. Okay. Okay. What's next? Oh, go ahead. Oh, yeah, absolutely. We're bouncing around. We haven't covered anything early. Empirical formula. Oh, you mean number 10?
Yeah.
Okay. Yeah, this one's actually easier than you might expect because empirical formula it is the lowest total number ratio, but any ionic compound, you're going to use the empirical formula, right? Because there is no such thing as a molecular formula for an ionic compound, because what happens with ionic compounds is you have like positive charge, negative charge, positive charge, negative charge, and then onwards to like, billions and trillions of atoms. Like if you have one salt crystal that's like this big, that's technically one molecule. I mean, but it's, ridiculous amount of ions that are present there. So with ionic compounds, we always do the lowest total number ratio. To figure out the empirical formula then, all we have to do is look at the individual ions. So what is the ion that is formed by magnesium. What's the charge of a magnesium ion? 2 plus. What's the charge of a fluorine ion? Yeah. So when you're writing these formulas, you want to balance the charges. The total positive has to always be equal to the total negative. In that case, how many magnesiums and how many fluorines do you need? 1 and 2. So Mg F2. The subscript tells you how many you have, whereas the superscript told you what the charge was. You can cross it. Just be careful. If you cross it, make sure that the subscripts aren't divisible by the same number. Also, make sure that you don't include the like positive or negative. So I'm not a huge fan of the whole crisscross thing, but I can give you an example of a time where you might want to be wary. Let's say you had something like this. You had lead, and it had a 4 plus charge, right? And then you had oxygen with a 2 minus charge. If you crisscrossed them, you might be like, oh, well, it's Pb2O4. But the problem with that is that 2 and 4 are both divisible by what? 2. The actual formula here to make it a lowest whole number ratio is PbO2. Does that make sense? So MgF2 is the correct answer, or E. All right. Any other questions? Which one? 13? Sure. So 13, it says element X has 3 naturally occurring isotopes. The mass and the abundance of the isotopes are as follows. What is the average atomic mass? Okay, so in a case like this, the easiest way to deal with this is to go ahead and to recognize what you're doing is you're taking a weighted average. Okay, this is actually how your grades are calculated, by the way. You're taking a weighted average. So the quote unquote, there's the mass of it, and then there is the weighting factor, essentially. In other words, if I have a higher percentage of 1, that's going to play a bigger, that's going to have a bigger role in the average, right? Yeah. So if a much higher percentage of a small molecular weight, that's going to cause this lower weight to dominate in the average. So basically, what I do is I essentially take the 37.919 and I can multiply it times 5.07, the percentage, okay? And just because I'm lazy, I don't think I'm going to write percent anymore. Then I'm going to take the 39.017 rather, and I'm going to multiply by its percentage, 15.35. And then I'm going to take the 42.111 and I'm going to multiply that times 79.58. So then what you're going to do is you're going to multiply each of those. They're going to get 3 answers, and you're going to add them up. What do you get for your answers? What'd you say? 41.42. Well, basically, if you multiply these out and you add them up together, you would get 4,142, okay? All you then have to do is divide by the total abundance. What's the total abundance? 100. So I divide this by 100%, and that's going to give me That's going to give me my 41.42. Now, in truth, you could actually, with this one, you could actually, if you know anything about averages, not even bother do any of the calculations. And I'll tell you why. You look at the percentage of the 42.111. Almost 80%, okay? The average is going to be a heck of a lot closer to that number than it is to be any of the others. If you look at the next one, it's like 39.68, 39.07. No, it's definitely going to be a lot closer to the 42. So 41 is the only one that really makes sense in that context. But if she was trickier and gave you ones that were like, 25, 36, and, something like that, then you might have to just kind of calculate it because it wouldn't be certain, Okay. Next question. 19. Okay. Now it says, consider the following reactions. Which is the order of increasing activity for these metals? Okay, so here's the thing about activity of metals. The most active metal wants to be charged, wants to be positively charged. When you talk about activity of metals, you're talking about the one that's most easily oxidized. So you don't have to think about it too much, but essentially, another way to think of it that's maybe a little bit easier is that the least reactive metal will always want to be by itself, okay? So if I look at the reactants for the first reaction, the least reactive metal wants to be by itself. So you look what happens at the end of the process. So there is a reaction that occurs. What metal ends up by itself? Ag. So what's less reactive? Ag is the less reactive element. All right, then I look between copper and zinc, there's no reaction. What metal ends up by itself? Zinc. So since zinc is the one that ends up by itself because there's no reaction, which one is less reactive? Zinc. So zinc is less reactive than cobalt. And then I see silver and cobalt. Which one ends up by itself? The silver, right? The silver ends up by itself at the end, which means silver is less reactive. So this tells me three things. I know that silver is less reactive than zinc. I know that zinc is less reactive than cobalt. And I know that silver is less reactive than cobalt. So yeah, it's A. Now, question, did you really need that last reaction? No, because if you already know that zinc is less reactive than cobalt, but silver is less reactive than zinc, then that would actually be sufficient to actually put together this series. Cool. 21? No. Okay, yeah, I can. All right, it says concentration of the species in 500 milliliters of 2.104 molar solution of sodium sulfate is blank molar sodium ion and blank molar sulfate ion. This is not so much a molarity problem as it is a writing ionic formulas problem. You need to be able to figure out what sodium sulfate is. What is sodium? And what charge does it have? Positive 2? Oh, positive 1. Yep. And what is sulfate? SO4. And what is the charge of sulfate? Yeah, 2 minus. All right, so what's the formula for sodium sulfate? Yeah, Na2, SO4. And whether you did crisscross or just figured out, okay, well, I need 2 sodiums to balance with the -2, either is fine, as long as you get that answer. So because there's 2 sodiums for every sodium sulfate, what's the molarity of sodium ion? Because there's 2 sodiums in every sodium sulfate, what's the molarity of sodium ion? The molarity of sodium sulfate is 2.104. So it's the molarity of sodium times 2. Yeah. Yeah. So, kind of give you kind of a point. If you wanted to show it via calculation, you could show it like this. Because molarity is moles per liter, right? So this is moles of sodium Na2SO4 per 1 liter, right? That's the definition of molarity. Molarity is moles per liter, right?
Yep.
So I could actually just be like, okay, well, I know that for every mole of sodium sulfate, I'm going to have how many moles of sodium ion? 2. And therefore, that gives me what? 4.208. And note that since that is the only choice that gives you that as your first answer is what? E. Yeah, so that is your correct answer. Yeah, moles of this cancel out, and I'm get moles of sodium ion per liter of solution. My molarity is 4.208 molar. Yeah.
The 500 milliliters, that was just like a diversion or something?
Yep, completely unnecessary information.
Question 31.
Yep. 31. So which electron configuration represents a violation of the Pauli exclusion principle? Okay, so the Pauli exclusion principle states that no 2 atoms. Oh, wait, actually, does somebody want to tell me what the Pauli exclusion principle states? Yes. Yeah, basically. Yeah. Officially, the definition is no 2 atoms can have the same set of 4 quantum numbers. But what that means is you can't have no 2 electrons, my bad, can have the same set of 4 quantum numbers. But what that basically means is that you can't have 2 electrons in the same orbital and have the same spin. They have to be opposite spins. Otherwise, that means they have the same 4 quantum numbers. So which of these violates the Pauli exclusion principle? B. Now, just out of curiosity, what principle does A violate? The Aufbau principle. And what rule does C violate? Hund's rule. Hund's rule basically states that if you go to a party and they have pizza, you don't be taking like all the pizza before everybody else gets some, right? Everybody gets some before you start taking seconds, okay? That's kind of like Hund's rule, but applied to pizza party, except in this case, it's electron configuration. So each orbital gets 1 electron before you start doubling up. Now, question, does D violate Hund's rule?
No.
No. Does it violate the Aufbau principle? No. Because all p orbitals in the same subshell have exactly the same energy. So it doesn't matter which one gets filled first, and it doesn't matter which one gets filled second, because they're equal energy. What'd you say? The only thing that E would violate would be the off-bow principle, because essentially, off-bow principle is basically, or it says that electrons will fill up the lowest energy orbitals possible in the ground state. So this would not be a ground state because the lowest energy, like the electrons would fill up this one, so 2 in here before filling up this one, 2 in here before going here. Very good, very good. Okay, cool. 16? Okay. And my online friends, please feel free to cut in if you want me to go over anything, okay? So 16, how many moles of GeH4 are needed to form 8 moles of GeF3H? According to the following reaction, if the product is obtained in a 92.6% yield. Couple of different ways to approach this problem. Essentially, is how many moles are needed to form 8 moles of GeF3H if the product is obtained in 92.6% yield. Now, GeF3H, this is how much I want to get. This is the amount. This is, you have to recognize that if I need to form this, and I know that I'm not getting 100% product, I have to take that into account. This is what you might be referring to as your actual yield. This is the actual amount that I want to get out of this. Because this is, it says how many moles of GeH4 are needed to form this amount. When I'm actually trying to form this amount, I need to actually add a little extra reactant, right? Because I can't just assume that all the reactant is going to be used up. I have to take that into account. I'm not using up all my reactant. It's not completely reacting. It's only giving me a 92.6% yield. So if this is the amount that I want to form, then this is my actual yield. Is what you're actually forming. Now, if it said how much could you expect to form, then that would be your theoretical. Well, I mean, like, it kind of depends on the wording, but if it says how much could you expect to form if such and such reactant reacted with such and such reactant, then you would say, okay, well what my answer would be your theoretical, it would be your theoretical yield. That's your theoretical yield. If it what? Yes, assuming a 100% reaction. Assuming 100% reaction. Typically, your actual yield is going to be the one that's given to you. Your actual yield is going to be the one that's given to you. So, there's a little clever way I like to do this particular problem, because as you remember, actual divided by theoretical times 100 is percent yield, right? Now I can actually convert my percent yield. I can say that percent means per 100. So I can say, well, my 92.6% is telling me that I will get 92.6 moles of product, the GeF3H. That's how much. That's the actual amount I will get from out of every 100 that I would expect to get if it went to completion. So then what I would do is I'd start with my 8 moles of GeF3H that is my actual yield that I'm going to try and get. So 8 moles. Of my actual GeF3H. And actually, I'm going to zoom into this. Yeah, GeF3H. I probably should have done that from the beginning, so my apologies. Better late than never, though. Moles, GeF3H. Actual. And so this is 92.6 moles that I would actually form, for every 100 moles that I would expect to form. And then from there, I can, and this would be expected. And then from there, I can just use the mole ratio in the balanced equation, which is the moles of GeF3H to moles of GeH4. It's really hard to write on this thing. H4. I apologize, I know this is a little sloppy. But in the equation, this has a coefficient of 1, and the other one has a coefficient of 4. And if you multiply that out, the answer that you get is 2.16. Now, alternatively, the other thing that you could do here is you could just convert the 8 moles of GeF3H straight to moles of GH4, and you would get the answer 2. But then you would have to think about, okay, but that's assuming 100% yield. I don't have 100% yield, so I'd have to add a little extra to make sure I get the 8 amount. So, okay, well, the answer that I get is 2, but I need a little bit of extra. Which one gives a little bit extra beyond 2? E, 2.16. So that you could use a combination of a simple calculation and a little bit of logic, or you can use this more complex calculation, but either way, you would get the right answer. Yes?
Question 36.
36. Says, based on the octet rule, magnesium most likely forms what type of ion? Honestly, this is basically just looking at the periodic table. So it's 2+, yeah. Basically, all the atoms are going to try to gain or lose electrons to be like the closest noble gas. Why? Because the noble gases have 8 valence electrons. So magnesium is closest to what noble gas? Magnesium is closest to what noble gas in terms of its number? Neon. And magnesium has 12 electrons, neon has 10, so it would lose 2 electrons, and therefore it would be +2.
What's the octet rule again?
Octet rule means that all atoms will either gain or lose electrons in order to have a full valence shell of 8 electrons. That's what octagon, 8. So that's why it's octet rule. Although there are exceptions to the octet rule. What are the exceptions to the octet rule? What'd you say? Boron, beryllium, and hydrogen. Those are the exceptions of not having or having less than 8 And there's also exceptions for having more than 8. And that would be any element in the third period or below, right? So, yeah, how many electrons does boron tend to like to have? 6. Keep that in mind because professors like to throw boron on these exams. Have you noticed that? Yeah, in the quizzes and other things, they'll throw boron a lot. Beryllium only wants 4. Hydrogen only wants 2, which means hydrogen will only ever form 1 bond. All right. Any other questions? Yes. Tw 25? Oh, that's a fun one. Okay. It says when 72 grams of metal at 97 degrees is added to 100 grams of water at 25 degrees, the final temperature is 29.1. What is the heat capacity of the metal? The specific heat of water is that. So with this, all you have to do is keep in mind that whenever you have heat transfer in a system, provided it's an isolated system, you can assume that all of the heat gained by one is lost by the other. So in this case, the metal is hotter, right? So it's going to lose energy, and the water is going to gain energy. All of the heat lost by the metal is going to be gained by the water, presumably. And that can be summarized in the following expression. It can be summarized as Q of the metal, or Qm, is equal to the negative Q of the water, H2O. Now, what is Q equal to? The amount of heat transfer. Basically, Q refers to heat transferred, essentially, or essentially the change in heat, change in energy with respect to heat. But what is the equation? Q equals what? MC delta T. So in this case, Q of the metal is going to be M of the metal, so MM, times the specific heat of the metal, Cm, times the change in temperature of the metal, delta Tm. And that's going to be equal to the negative Q of the water, which is the mass of the water, MH2O, times the specific heat of the water, CH2O, times the temperature change of the water, delta TH2O. At this point, all you have to do is go ahead and plug in the information. What is the mass of the metal? 72 grams. What is the specific heat of the metal? Nope. I don't know. I'm going to just call it question mark. Because that's actually what it's asking for, right? It says heat capacity, but the truth is it's specific heat capacity. That's when they say specific heat is actually short for specific heat capacity. And then, what about the delta T of the metal? Actually, it's final minus initial. So it's going to be, what's the final temperature? Yeah, 29.1. So 29.1 degrees Celsius minus the initial, which is 97, right? And that's equal to the negative mass of the metal, or mass of the water, which is what?
100 grams.
100 grams. I'm going to be lazy on steak pigs. I know I shouldn't, but. And what's the specific heat of water? 4 joule per gram degrees Celsius. And what's the temperature change of the water? Final minus initial, right? 29.1 minus 25. Now let me ask you a question. Do I need to convert these temperatures to Kelvin? Why not? So what'd you say? Actually, that's not why. The reason is because change in Celsius is the same as change in Kelvin. They have the same increment amount, but they start from different points. But if you did the change in temperature in Kelvin, all I would do is add 273 to the 29.1 and 273 to the 25.0. And so it would end up just canceling out anyway. But generally speaking, unless it's a change, we always use Kelvin in chemistry. We never use Celsius. And unless it's a change, and change we can get away with it. All right, cool. Then all you have to do is basically divide both sides by 72 and the change in temperature of the metal, and that will give you the specific heat. And what do you get? Yep, because that's whenever you're doing algebraically solving for something for algebraically, whatever you do to one side, you have to do to both other side as well. So 72 grams, divide by that.
You can divide with the delta T on the left side too, right?
Yep. So divide this by 72 grams and divide that by 72 grams. And the delta T on the left side is 29.1 minus 7 is 27. It's going to be like 68.9. No, 67.9. Negative 67.9. Okay, cancel this out. Cancel this out. And notice that the negative cancels out the negative. And C cancels out here. Grams cancels out over here. And I'm left with joules per gram degree Celsius, which is what I need anyway. And what's the answer? A? C, okay. 0.35 joules per gram degree Celsius. I'm going to assume that you have it correct because I don't have a calculator and I'm too lazy to get one. Is that what y'all got too? There's strength in numbers. Pun intended. That was bad. Sorry. Oh, I said there's strength in numbers. And I said, nope, I said pun intended. I was basically asking more people to calculate it. Yeah. Okay. Oh, 20. Got it. I was expecting something to come after the 20. Like 20. Like, no, just 20. All right. 20 says an aqueous ethanol solution is diluted 4 liters, giving a concentration of 0.04 molar. What was the concentration of the original solution? Whenever you see the word diluted, chances are you're going to be using the dilution equation, which is M1V1 is equal to M2V2, where M1, you can think, it really doesn't matter which one you use as the original and which one you use as the final, but I tend to like to use M1 and V1 as the original. So what was the original molarity?
0.0.
Nope.
Oh, we don't know.
Yeah, the original molarity is what we're looking for. We don't actually know what the original molarity was. What was the original volume? Yeah, 400 milliliters, right? What was the final molarity?
Do we have to convert that to liters?
Yes, you do. Yes, you do. I wasn't going to mention it until after we finished putting our numbers down, but yes. What's the final molarity?
0.0400.
Uh-huh. And the final volume? Uh-huh. Now, does it matter which one we convert, the 4 liters or the 400 milliliters?
No.
Yeah, it actually does not matter. You can actually convert the milliliters to liters and have them both be liters, or you can convert the liters to milliliters and have them both be milliliters. In this case, though, if you go ahead and calculate that, you should get an answer of 0.4. Yeah, so like let's just say if we converted this to liters, this would be 0.4. This would be 0.4 liters. And then all you'd have to do is divide both sides by 0.4 liters, and that would give you your answer. All right, what's next on the agenda? 34. Of the following elements, which has the largest first ionization energy? So all of this comes back to effective nuclear charge. And if you understand how to estimate effective nuclear charge, then everything else is going to make sense to you. But in short, when you're talking about the first ionization energy, the trend in first ionization energy is it tends to increase going up, and it tends to increase going across. Why is that the case? Well, basically, it's the case because I said so. No, I'm just kidding. It's the case because as you go down, the size of the atom gets bigger, right? And so I'm going to take an example from football because I love football. All right. Where is it going to be easier to take away a football from a running back? If he's got it close to him like this, or if he's going like this? Like, yeah, when he's like holding it out in front of him, right? The farther away something is, the harder it is to hold on to it. And that's the same thing with the atom with its electrons. So with these large atoms, the ones that have the electrons that are furthest away from the nucleus, it's easier to pull those away. So as you go down, ionization energy goes down because it requires less energy. Now as you go across, ionization energy increases. And this is because effective nuclear charge increases. Because essentially, if you looked at, like, for example, let's take a look at the periodic table. Let's say we have, so you have a hydrogen, right? And then we have this periodic table. It looks like this, kind of like, yeah. Okay. Okay. Sorry. So let's say this is sodium, okay? And then you got a magnesium, and then you got aluminum. Oh well. Yeah, this is aluminum. Let's give it an extra layer here. This is aluminum, silicon, phosphorus, sulfur, chlorine, and neon. Okay. So effective nuclear charge, sometimes written as the effective, is the number of protons in the nucleus minus the number of shielding electrons. So it's basically the protons minus the shielding electrons. Now, the thing is, the only electrons that are capable of doing any shielding are inner shell electrons. Valence electrons don't really shield effectively. So for sodium, how many shielding electrons are there? How many inner shell electrons are there for sodium?
2.
10. Yeah, because the previous noble gas before sodium is what? Neon, right? So if you think about, like, here's your sodium nucleus, right? You have 2 electrons in the first shell, you have 8 electrons in the second shell, and then you have 1 electron in the third shell. Okay? This 1 electron's not doing any shielding. It's not shielding very well. So only the inner shell electrons are capable of shielding. So with sodium, the number of protons it has is 11, right? And the shielding electrons it has is 10. So that gives you an effective nuclear charge of +1. In the previous noble gas, because the number of electrons in the previous noble gas the number of electrons in the previous noble gas is the number of electrons in the inner shells. So for magnesium, once again, the number of shielding electrons is how much? 10. It's 10. Same as sodium, because they both have the same previous noble gas. So it's going to be 12 minus 10, and that's going to give you a +2. And then for aluminum, how many shielding electrons does it have? It has 13 protons. It has 10. See the pattern? So as you go across, the number of shielding electrons does not change. It's still 10. It's still 10 each case. So what happens is the effective nuclear charge, the amount of pull, the amount of attraction that the nucleus exerts on the outermost electrons gets stronger and stronger and stronger, which is why it's pulling those outer electrons in tighter and tighter and tighter, which is why, which of these is going to be the smallest atom? Magnesium, sodium or chlorine?
Chlorine.
Chlorine's going to be much smaller. Even though it has more protons, it has more electrons, the effective nuclear charge is a +7, 7 times what sodium is. So it's going to pull those electrons in much tighter, and chlorine's going to be a much smaller atom than sodium. Does that make sense? So effectively, and the same thing is true with ionization energy. So if something has a higher effective nuclear charge, is it going to be easier or harder to pull an electron away? If something has a higher effective nuclear charge, so in other words, like chlorine has an effective nuclear charge of 7, right? And sodium has an effective nuclear charge of 1. Which is it going to be more difficult to pull an electron away from? The 7. So as you go across, ionization energy increases because effective nuclear charge increases. As you go across, atomic size decreases because effective nuclear charge increases and pulls them in more tightly. Yep. So as you go across, electronegativity increases because effective nuclear charge increases. And likewise, as you go across from left to right, electron affinity increases because electron affinity is the attraction for electrons, right? As you go across, effective nuclear charge increases, so there's more attraction for electrons. Does that make sense? So, I'm sorry? Sure. Let me actually go ahead and I'll just draw it out here. So ionization energy increases going across because effective nuclear charge increases and there's a stronger attraction. Electron affinity increases going across because effective nuclear charge increases. If it has a stronger effective nuclear charge, it's going to be more attractive to electrons. The nuclear charge is positive. electron affinity. And let me actually do a different color. I'll do red. And electronegativity increases going across because electronegativity and electron affinity are similar, but electronegativity refers to the attraction of two electrons when it's part of a bond. So in other words, if something is bonded to something else, which one is more attracted to electrons? Well, the electronegativity will tell you that. But if you want to know simply what atom that's by itself is more attracted to electrons, electron affinity is going to tell you that. Does that make sense? They're almost always the same. There might be some subtle differences. Electron affinity has a few weird disturbances, shall we say. And then the only one that is the opposite is which one? Yeah, atomic size, atomic radius. Atomic radius is atomic radius or atomic size. It's actually going to increase the other way. And I'll be honest, you don't actually have to understand effective nuclear charge to know what the trends are. But it is true that if you understand effective nuclear charge, you could figure out the trends without even having them memorized. So that's the advantage of understanding it. But at this point, final exam's coming upon you. Do whatever you feel is most effective for you. No pun intended. Okay. All right. So in that case, what is the answer for 34? B, nitrogen. That's correct. It's the furthest up and the furthest to the right. No. Wait. Yes. Yes, it would be. Very good. Not sodium. Chlorine. Yeah. 33 would be B as well. Oh, let's just do 35 just for giggles. Also, it's a weird, okay. It's a weird thing about electron affinity that the more negative electron affinity is the higher or greater electron affinity. So when it says what is the most negative electron affinity, that's really saying what is the greatest electron affinity. So which one of these has the greatest or most negative electron affinity?
Chlorine.
Chlorine, yeah. How do you define electron affinity? Electron affinity is defined as the amount of energy released when 1 mole of an element accepts, or when 1 mole of isolated gaseous atoms accepts 1 mole of electrons to form a negatively charged gaseous ion. So the amount of energy released when 1 mole of a gaseous atom accepts electrons to become 1 mole of gaseous negative 1 ions. It's a weird. It's the atom that's most attracted to electrons. If you were actually to have a table of electron affinities in front of you, you would see that, like, for example, oxygen, or rather sulfur here sulfur here might have an electron affinity of like negative 200, and chlorine's going to have an electron affinity of negative 353 or something. You know what I'm saying? So it increases as you go across, or it becomes more negative as you go across, more negative as you go up. But as you go to the right towards chlorine, and then as you go up, yeah. Although it is an odd fact about electron affinity that fluorine actually has a lower electron affinity than chlorine for some reason. But don't worry about that, because you're not going to be expected to know the exceptions. What'd you say? Yeah. No, this is something I'm 100% confident. She will not ask you to distinguish between the electron affinity of fluorine and chlorine. Generally speaking, you just have to know the general patterns. Increases going to the right, increases going up for electron affinity, ionization energy, and all the rest of them. Okay, somebody had a question on a different number. 47. Ooh, it says 50.75 gas occupies 10 liters at STP. 129.3 grams of the gas will occupy blank liters at STP. Okay, so there is an easy way to do this, and there's a hard way to do this. Intuitively, this is two sets of conditions, right? The hard way to analyze this would be to basically say, well, it's two sets of conditions. P1 V1 over N1 T1 is equal to, excuse me, T2 V2 over N2 T2. So here's the deal. STP is standard temperature and pressure, right? So what's staying the same here? Temperature and pressure. So this is just volume over moles is equal to volume over moles. Now here's the thing. What is the formula for moles? Mass over molar mass. So I can write this as volume over mass over molar mass is mass 1 over molar mass is equal to volume 2 mass 2 over molar mass. But here's the thing, the molar mass is the same, right? So I can really actually just eliminate this from consideration. So I can just basically say volume 1 over mass 1 is equal to volume 2 over mass 2, cross multiply and solve. So yeah, 50.75 over 10 liters is equal to 123.9.3 over 15 liters, or over X liters, I don't know how many. And then just cross multiply and solve. And yes, you'll get like the 25.5, right? So
What was the easy way?
that was well, the easy way is basically just recognizing that because 1 mole of a gas, no matter what it is or like the moles of a gas are proportional to the volume. That the mass of a gas is going to be proportional to the volume in the same way, and so you could just basically, instead of doing all this derivation, setting this up and then writing this down, just recognizing that you could just jump into the ratio right away. Sorry. Yes. 48. The volume of 0.65 moles of an ideal gas at 365 torr and 97 degrees is blank. So So yeah, this is just a PV is equal to nRT one. The only thing is you have to convert this to ATM, so you basically say 365 torr. If you're nerdy enough, like me, and you actually have the other ideal gas law constants memorized for all the different units, you wouldn't have to do this. You could just use one of the other ideal gas law constants. But if you're not that nerdy, then you're probably just going to have to do this. 760 torr is equal to 1 ATM. Bam. 365 divided by 760. It's going to be something. A little less than half. About 0.4 something or other. 0.48 something maybe. I don't know.
Yeah, you got it correct.
And then the 97 degrees, you have to make sure that you add 273. And that's going to make this 370. And then all you have to do at that point is plug in all the information and solve for the volume. So V equals nRT over P. So moles, 0.65. I'm going to do something that you should never do because I'm feeling lazy and I apologize. I'm not going to put my units. So 0.65 moles, and I don't recommend this for the exam. I am a trained professional. Do not try this at home. So let's see. 8206, right? Yeah. 370. All over pressure. Because there is actually a valuable reason for writing your units as well. If you look at your units and they don't cancel out properly, such that you end up not getting the right thing, or so that your unit's not the right unit, then that's a sign that you messed up. Also, if you don't write your units down, there's a good chance you overlook the fact that the units from 0.08206 liter ATM per Kelvin mole does not match with 365 torr, right? So write your units down. Don't be like me. And you multiply and divide that. That's going to give you, would you say D?
Yeah.
That sounds about right. Yep. Yes.
I was having the CHEM, the practice test for the ideal gas problem,
Uh-huh.
and there was some that asked for the mass of whatever, like finding the mass.
Yeah. In case where it asks you to solve for the mass, all you do is solve for the moles first, and then convert the moles to grams.
So you multiply, right?
Multiply by the molar mass, yeah.
Yeah.
If it asks you for the density, then you can simply take the grams divided by the volume. So basically, if you might have to, if it gives you like the grams, or if it gives you the moles, you might have to solve for the volume and then convert the moles to grams and then divide the grams by the volume. Or if it gives you the volume, you may have to, if it gives you the volume, you can solve for the moles, convert that to grams, and then divide the grams by the volume. That'll give you the density. There is a way to manipulate the equation. There's an alternate version of this equation. Remember how you said that pressure times volume, or moles, is equal to the grams divided by the molar mass, mass divided by molar mass? You could actually write that down here and say, well, PV is equal to mass divided by molar mass, RT. And if you multiply both sides by the molar mass, that gives you the pressure times the volume times the molar mass is equal to the mass times RT. And then if you wanted to solve for the density, you could divide both sides by volume because mass divided by volume is density. And that gives you PM equals dirt. DRT, dirt. So those are alternate forms of the ideal gas law you could use. But you can also just use the original form and just do a little extra calculation if you don't remember those other versions. Any other questions? We got 15 minutes. Yeah, no problem. You're like, I'm done with chemistry. That's enough for me.
I'm good now. Thank you. I appreciate it.
You're welcome. Any other questions? Wavelength and frequency, yep. Okay, the energy of a photon that has a wavelength of 13.2 nanometers is blank joules. So there's two equations that relate frequency, wavelength, and energy. There's the speed of light is equal to the frequency, which is typically kind of looks like a cursive letter V, but it's actually a Greek letter called nu, which another couple variants in the coronavirus will have nu. And then after nu, there's going to be lambda, right? And lambda looks like a cursive L, but that's your wavelength, basically. Yeah, actually, I should try to draw that just a little bit differently. But it actually kind of looks like a wave. So frequency times wavelength is equal to the speed of light. The other one is energy is equal to Planck's constant, h, times the frequency. Now in this case, I'm given the wavelength, and I'm asked to solve for the energy. Notice where the wavelength is. It's here. Now c as the speed of light is probably a constant your professor will give you, but it's 3.00 times 10 to the 8th meters per second. And Planck's constant is another constant which would probably be given, but it's 6.626 times 10 to the negative 34 joule seconds. Notice the 3 sixes in Planck's constant? Further proof that chemistry is the devil. No, I'm just kidding. Sorry, I thought it was funny. All right. Anyway, so we'll go ahead and plug in our nanometers and our speed of light and solve for the frequency. But what's the problem? What'd you say? It's the it's the nanometers. Nanometers doesn't match with meters, right? So I have to actually first do a little conversion. 13.2 nanometers. And so yes, unfortunately, you didn't think you had to memorize those, did you? But you do. So nanometers to meters, what does nano mean?
-9?
10 to the negative 9th. So nano means 10 to the negative 9th. So 1 nanometer is 10 to the negative 9th meters. Put a 1 in front of the unit with the prefix and put the meaning of the prefix in front of the base unit. And that's going to give you 1.32 times 10 to the negative 8th meters. Now I can plug that into C is equal to nu lambda, and essentially I have 3.0 times 10 to the 8th meters per second is equal to the frequency times the wavelength. That's my terrible French accent, by the way. All right, so divide both sides by 1.32 times 10 to the negative 8th, and you'll get the frequency, which in this case is... Can you repeat that? That sounds good. 2.27 times 10 to the 16th. 2.27 times 10 to the 16th. 10 to the 16th. 10 to the 16th what? Yeah, because you're dividing by meters, right? It cancels out. So strictly speaking, it's 1 over seconds, but what it actually means is waves per second. So it's that many waves per second are passing by a particular point. So now I can go ahead and plug this into the E equation. I'm going to change the color of my pen. What's green? Where's green?
Right there.
Dark green? There we go. I'm colorblind. I actually truly am. So sometimes don't know. All right. So then I'm just going to plug in Planck's constant, 6.626 times 10 to the negative 34. Joules seconds, joules times seconds. And notice since this is 1 over seconds, seconds is going to cancel out. 2.27 times 10 to the something or other, 16th, seconds to the negative 1. Ah, get back. There. It won't let me close it up. That's okay. All right. So then you just multiply those and you'll get your answer. And I don't know, it gives you something. Unfortunately, there's two answers that are too similar. It's either going to be B or E, but I don't know which one. E? So, I'm going to trust you. Trusting you now. All right. E it is. And there we go. Make sense? All good? Cool. Ooh, this is a fun one. 28. All of the orbitals in a given electron shell have the same value of the what quantum number? What did you say? Principal. Very good. Principal quantum number. You're absolutely right. Quantum numbers. So there's 4 quantum numbers, remember? They're kind of like an address for an electron, okay? So there's the principal quantum number. There's the angular momentum quantum number, or azimuthal quantum number. There's the magnetic quantum number. And then there's the spin quantum number. I'm going to use text here. But the principal quantum number basically tells you the energy level or shell. In other words, how far is it from the nucleus? The angular momentum quantum number tells you the shape of the orbital. Because the shape of the orbital is dependent upon the angular momentum of the electron. The M sub L tells you the orientation in space. In other words, which orbital? So the shape of the orbital will indicate the subshell. A P subshell, it's peanut shaped, it's a P subshell, or an S subshell, it's spherical. but the M sub L tells you which specific orbital it is. So, for example, if you have the p orbital, you can either have it go up and down, it can go left and right, or it can go in, out. Like that, coming in and out at you. So there's those three different orientations, up, down, side, side, in, out. And each one of those has a different orientation. This is why a p subshell has three different orbitals. It has three different orbits or pathways that can be followed. So the M sub L, the M sub L quantum number tells you which pathway, which orientation is it stuck in. And then the M sub S is the spin quantum number. And that just tells you which way is it spinning, essentially, clockwise or counterclockwise. And technically speaking, it's not really clockwise or counterclockwise per se, but you can think of it that way, just like to simplify it. So it's kind of like an address for an electron. With these four quantum numbers, you can tell exactly where or you can tell roughly where an electron is and what its behavior is. So, and by the way, I do want to mention this because this is important. A number of students come back to me after Seagal's exams always, and they say, you know, I was expecting all this calculation stuff, and there were calculations on there, but there was a lot of terminology and definition questions too, and I didn't prepare for it, and I really did poorly on those questions. So I would strongly recommend that you take the time to know the terminology. Now, if you're kind of wondering like, oh shoot, how do I figure out what the terminology is at this point? Is by like, you know, go through all my notes or whatever. Well, the good news is that we actually have a real easy way for you to do this. So, and actually, I'm going to go ahead and review for you just how to find us. But if you go to www.tccd.edu, if you go to academics, and then you scroll down to where it says academic help, under labs and tutoring, and then go to virtual learning commons in Canvas. Once there, you can click on science support. Don't click on a campus, just click on science support. And this will give you, scroll down past the online tutoring schedule, all the way down to where it says online science resources. From there, go to general chemistry, and I know that's a lot of clicks, and I'm sorry. I don't like the fact that they made it that complex either, but general chemistry 1, 14, 11. So these concept reviews are your best friend. If you want to go through all of the different definitions and terminology, this is the place to review. For example, if you want to, let's say, here we go, let's do this. What's matter? What's a pure substance? What's an element? What's a compound? What's a mixture? What's homogeneous versus heterogeneous? What are physical properties or chemical properties? What are the different types of energy? You know, what are significant figures? What is accuracy versus precision? What is random versus systematic error? Atoms and elements, or at least let's say thermochemistry, because this one has some. What is work? What is heat? What is energy? What's the first law of thermodynamics? Is usually something you throw on there with regards to that. What's a state function? Usually they have a question about state functions versus path functions. What is enthalpy? What is calorimetry? What is heat capacity? So knowing, like, this goes through all the definitions, gives explanations and such. These, I've had students actually go through and come in and have me print off a copy of each one of these and just kind of like go through them all or whatever. And they've said it's really helped them. This is back before we had them online. They said it really helped them do awesome on their final exam. So these summary pages are really useful because they don't just contain the definitions, they also contain all the formulas. So it kind of help you review all that stuff. Well, it was fun hanging out with y'all for 2 hours doing nothing but chemistry. I'll let you go for now, but thank you so much for coming, and I wish you all the best in your final exam.
Thank you. Bye.
Bye.